Good evening. I want to begin with a catastrophe. Not one that happened, but one that should have happened if the older physics were the whole truth. An atom, we learned, is a small positive nucleus surrounded by negative electrons. Opposite charges attract. Elementary. In the classical picture, the electron circles the nucleus, and a charge that accelerates must radiate energy. Classical electrodynamics, then, gives a grim prediction. An orbiting electron should lose energy, spiral inward, and fall into the nucleus in an astonishingly short time, about 10 to the minus 11 seconds for a hydrogen-like atom. Every atom should collapse. Matter should not persist. Chemistry should be impossible. And yet, here you are. Here am I. Here is this desk, this chalk, this very air we breathe. So something is protecting the atom. Something prevents the electron from taking that fatal plunge. Tonight I will show you what that something is, though I warn you, the answer will force us to abandon almost every intuition we carry from the visible world. Let me start not with atoms, but with light. For a long time we thought we understood light perfectly. It is a wave, an electromagnetic wave, and experiments with interference and diffraction proved the wave character beyond doubt. Maxwell's equations described these waves with extraordinary success. And yet, there was an experiment that refused to fit the story. You shine light onto a clean metal surface, and electrons can be ejected. This is the photoelectric effect. If light were only a continuous wave, energy smeared out like water from a fountain, you would expect bright light to eventually knock electrons free, even if the color is red. Dim light should do the same, only more slowly. But that is not what happens. For each metal, there is a threshold frequency. Below it, no matter how intense the light, electrons do not come out in the ordinary photoelectric effect. Above it, even very dim light produces electrons immediately. And the maximum energy of those electrons depends on the light's frequency, not its brightness. Brightness mainly changes how many electrons are emitted, not how energetic each one is. The simplest explanation is that light delivers its energy in discrete packets. A single packet of light of frequency nu carries an energy E equals h times nu, where h is Planck's constant. One packet of violet light carries more energy than one packet of red. If each packet lacks enough energy to free an electron from the metal, increasing the intensity only brings more underpowered packets. Nothing is liberated. This was my proposal. Light, so wave-like in its interference, also behaves as if it arrives in quanta. Today you call these quanta photons. It was unsettling. but nature was only beginning her revelations. If light, which we called a wave, can behave like a particle, might the reverse also be true? Might particles behave like waves? In 1924, Louis de Broglie proposed exactly this. To every particle of momentum p, he assigned a wavelength. Lambda equals h over p. The larger the momentum, the shorter the wavelength. But the wavelength is always there. At first, this sounds like philosophy. But it becomes physics the moment we see what it explains. Consider a violin string. It cannot vibrate in just any pattern because it is fixed at both ends. Only waves that fit are allowed. A half wavelength, a full wavelength, and so on. These standing wave patterns are the harmonics, the allowed notes. Now replace the string with the electron in an atom. Do not imagine a tiny planet in a tidy orbit. Imagine instead a wave-like state described by a wave function. Something that can form standing patterns around the nucleus. If the wave function must be self-consistent, only certain patterns are permitted, and those patterns correspond to discrete energies. This is the deep idea behind atomic stability. The electron is not free to have just any energy, or to radiate continuously downward. There is a lowest allowed energy state, a ground state. Once the electron is in that state, there is simply no lower state available for it to fall into. Bohr first captured stability by postulating quantized orbits. Later, Schrödinger wrote an equation whose solutions produced those discrete energies naturally. The allowed states are the standing wave solutions of the atom. But if electrons are wave-like, spread out in space, what does it even mean to ask where an electron is? This question leads to something profound, something Werner Heisenberg formulated sharply, and which troubles me to this day. Here is one way to feel the logic. Imagine you wish to locate a ship on the ocean at night in dense fog. You send a short blast from a foghorn. A short blast lets you time the echo precisely. You get a sharp distance. But a short blast has no definite pitch. It is a mixture of many frequencies. If instead you send a long, pure tone, you know the frequency precisely, but the sound is spread out in time, and your distance estimate becomes less sharp. This is not an accident. It is the mathematics of waves. A wave localized in space or time must contain a spread of wavelengths and frequencies. In quantum theory, momentum is tied to wavelength. So a state sharply localized in position must contain a spread of momenta. There is a simple inequality behind this. Delta x times delta p is at least h bar over 2, where h bar means h divided by 2 pi. It is not a defect of our instruments. It is not that we have not tried hard enough. It is a feature of how wave-like states are built. In quantum theory, the question, What is the exact position and exact momentum at the same time is not merely difficult. It is not a question nature answers. Now we can return to the catastrophe with which we began. Why does the electron not collapse into the nucleus? Because to confine the electron to an extremely tiny region, say as small as the nucleus, would force delta X to become extremely small. Then delta P must become extremely large. A large spread in momentum implies a large typical kinetic energy. In other words, squeezing the electron costs energy. At the same time, spreading the electron far out costs electrical potential energy because the attraction to the nucleus grows weaker. The stable atom is a compromise, not a classical orbit, but a quantum state whose size is set by the balance between electrical attraction and the kinetic energy cost demanded by uncertainty. The result is a characteristic scale on the order of 10 to the minus 10 meters, an angstrom, the size of atoms, and the scale of chemistry. And what of solidity? Why does your hand not pass through this desk? When you press your hand into the wood, the electrons in your atoms are forced closer to the electrons in the wood's atoms. Two things then matter. First, electrical repulsion. Like charges resist being pushed into the same region. Second, the Pauli exclusion principle, which I will describe in a moment. Electrons cannot all pile into the same quantum state. So when you try to compress matter, electrons are forced into higher energy arrangements. That energy cost appears to you as a resisting force. The desk pushes back not because atoms are hard little billiard balls, but because the allowed quantum states of the electrons resist being squeezed into the same place. Classically, you might call it solidity. At bottom, it is electromagnetism, shaped and reinforced by quantum rules. But quantum mechanics is stranger still than stability. It also tells us how to calculate. To make predictions, we use quantities that do not directly correspond to anything we can see or touch. We work with probability amplitudes, complex numbers that have both a magnitude and a phase. Think of it this way. Suppose an election where each vote is not just a count but an arrow. It has a size and a direction. To combine votes, you must add arrows. Sometimes they reinforce. Sometimes they cancel. The final result depends not only on how many votes exist, but on their relative directions. So it is in quantum theory. For every possible way an event can occur, the theory assigns an amplitude. We add all the amplitudes for all the indistinguishable alternatives. Only at the end do we obtain a probability by taking the magnitude squared of the total amplitude. Max Born taught us to interpret the magnitude squared of the wave function as a probability density. The rule works with astonishing precision. But the meaning of the amplitudes, the meaning of the wave function itself, remains to me deeply mysterious. Nowhere is this mystery more vivid than in the experiment that refuses to make sense, the two-slit experiment. We fire electrons toward a barrier with two narrow openings, and behind it we place a screen to record where each electron arrives. Each electron is detected as a whole, one spot, one click, never half an electron. In that sense, it is particle-like. But if we repeat the experiment many times, building up a pattern of impacts, we do not get two simple clusters behind the two slits. We get stripes, bands of many impacts and bands of almost none. This is interference, the hallmark of waves. How can a particle, fired one at a time, build an interference pattern? The quantum rule answers: the electron's amplitude to arrive at a given point is the sum of the amplitudes for the two alternatives, through slit A and through slit B. Where the phases reinforce, the probability is high. Where they cancel, the probability is nearly zero. Very well, so we decide to determine which slit the electron passes through. We place an apparatus that can, in principle, record the path. And now the interference disappears. The pattern becomes what ordinary particles would give, essentially two broad clusters. This is not because a human mind looks. It is because to learn the path, the electron must interact with the apparatus in a way that leaves a trace, some physical record. That interaction makes the two alternatives distinguishable, and the delicate phase relationship between them is destroyed. When the alternatives are distinguishable, the amplitudes no longer combine to interfere. You may summarize it like this: you can have interference, or you can have which path information, but you cannot have both at once. There is another principle, equally strange and even more consequential, that governs electrons. Wolfgang Pauli discovered it. No two identical electrons can occupy the same quantum state. Be careful with the words. This does not mean only two electrons in an energy level. An energy level can contain many distinct states. But each distinct state, each orbital, each set of quantum numbers can be occupied by at most one electron. Because electrons also have a property called spin, two electrons can share the same spatial orbital only if their spins are opposite. After that, that particular state is full. This single rule builds the architecture of the periodic table. It forces electrons in many electron atoms to spread into different states. And because different atoms have different numbers of electrons, they fill these states differently. That structure determines chemical bonding. Without Pauli's rule, the richness of chemistry would collapse into monotony. Finally, the quantum rules allow us to read the universe. When an atom changes from a higher energy state to a lower one, it emits a photon whose energy equals the difference between the two states. Because the allowed energies are discrete, the emitted light has discrete frequencies, spectral lines. Conversely, atoms can absorb photons of those same characteristic frequencies, producing dark absorption lines in an otherwise continuous spectrum. Each element has its own pattern of lines. Hydrogen has one signature, sodium another, iron another still. So when we take the light from a star and spread it into colors, we find a pattern of lines, bright or dark, that acts like a fingerprint. From starlight alone, we can infer composition, temperature, and more, even for objects many light years away. And now I must end with honesty. I have shown you the rules: quantization, wave-particle duality, uncertainty, amplitudes, exclusion. With them we can account for atomic stability, chemistry, and the behavior of light with extraordinary success. But we do not know why nature chose these rules. We do not know what the wave function is, in the same concrete sense that a field or a particle in classical physics seems to be. We do not know whether the theory is complete, or whether there is a deeper description beneath it. My colleagues disagree fiercely about interpretation. Some are satisfied to speak only of measurement outcomes and to refuse questions about what is really happening. I am not satisfied so easily. I suspect there is something deeper, some underlying account in which chance is not the final word. But I may be wrong. Perhaps probability is woven into the foundation of the world. What I can say with certainty is this: quantum mechanics is not optional. Every atom in your body, every photon that reaches your eye, every chemical reaction that sustains your life follows these rules. The universe is quantum at its foundation, and we, through careful experiment and stubborn reasoning, managed to glimpse it. That itself is remarkable. Thank you. I welcome your questions.